Welcome to the Building Science Podcast.
Welcome to the Building Science Podcast.
Bringing the human factor to construction, design, and architecture. Brought to you by Positive Energy in Austin, Texas.
Greetings all and welcome back to the Building Science Podcast. I'm Michael Walker.
And I'm Christoph Irwin.
And as you know, this podcast is dedicated to the weird science behind the construction of your home and the architecture. And we really focus on the human factors of that process and how the way we build homes and think about homes can be more centered around you because you're in the space, you're living in it, and it makes sense to think about you when we build it.
That's what it's built for.
So diving right into the heart of human factors, let's think about what the heart actually does. And stay with me for a minute. The heart circulates fluid throughout your body, right? It circulates blood. And blood is mostly water. And that fluid actually has a lot to do with how hot or cold you feel. It maintains this homeostatic temperature that your body operates at in an optimal way. And that process is what we all think of as radiation, right? The movement of heat to a cooler place.
Right.
It's the second law of thermodynamics, and it's one we all learn about when we're young, but when we get older, we stop really seeing its application in day-to-day life, even though it's occurring all around us all the time.
So it's occurring all the time. We might think, oh no, when I cool down, I sweat. Well, when radiation is no longer cutting it for you, you're using evaporative cooling by covering your body with water, and it'll cool you down. But all the time. So most of us are not sweating all the time, but all of the time your body is regulating your skin temperature to keep your core at a steady temperature so that all the chemical processes can occur efficiently.
Right, and so if we think about our blood actually maintaining that temperature, right? It's maintaining a surface temperature. Because if our body cooled itself by only regulating the air temperature, our entire cooling process would take place in our lungs, which just seems absurd, right?
Right, exactly.
And it's not so dissimilar with a home. If you think about your air conditioner's job, you're moving around this really inefficient liquid, which is air.
Fluffy.
It's very fluffy. And its job is to heat and cool the house. Does that seem a little counterintuitive to you? Doesn't it make more sense that if the surfaces were actively cooled and heated, that you could be a lot more comfortable, just like the human body works?
That's exactly right. So let's make something very clear. We're not talking about biomimicry. We're not saying we need to design houses to mimic the way the body works. What we're saying is, what we've been saying all along in this podcast, is that we need to design the space that we're in to make ourselves comfortable. And what this means is we use the space around us in the way that is synergistic with the way the body works. And what the body is doing, it is saying, I wish to regulate my temperature primarily through radiation. What this means is I wish to regulate my temperature primarily through interacting with the temperatures of the surfaces around me. So I think it'll be important at this point to jump in and make sure we define exactly what we're talking about when we talk about radiant heating and cooling in a home. It's also known as thermally active surfaces in buildings. And what it is using water, right? So like in the heart example that Michael just gave, right? Our blood is mostly water. Our bodies are mostly water. Everything is mostly water. Beer is mostly water. So what we're doing is we're circulating water through the mass of the building to regulate the surface temperature. And what does that mean? Let's go back to the air conditioning conversation we had last week. Let's say I have radiant cooling loops. So I have PEX, cross-linked polyethylene tubes, plastic tubes, let's say, embedded in the walls or ceiling of the building. And what happens is as the heat, let's say it's in the ceiling, as the heat is trying to move through the ceiling assembly, the heat from the sun, the heat from the outdoor conditions, it encounters those loops. Heat moves to cold. Remember, heat doesn't rise. Heat moves always to cold. So the heat gets channeled by natural laws of physics into the fluid, the radiant cooling fluid, and it moves through the pipe and gets collected and rejected to an outdoor unit, or collected and rejected into the ground or into a water tank There's lots of places that you can reject it. So basically, radiant heating and cooling is using water instead of air to absorb heat in the summer or to absorb cooling in the winter.
So essentially the space, or the building itself, I should say, never gets hot or cold.
That's exactly
depending
right.
on the outdoor forces, right?
Right. And I do want to correct myself. It doesn't absorb cooling as much as it radiates heat to the cold surfaces in the winter.
Makes sense.
Yeah.
How would this even work in a house? How would you install this? It doesn't seem like many contractors do this, and there are probably some good reasons for that.
Well, I think the reason we don't use radiant in our buildings more commonly actually has a lot to do with contractors, and more so probably with materials, meaning that the original radiant systems that went in, not the original, these go back thousands of years, but the modern ones that were actually competing with the forced air systems back in the mid-20th century, there were material problems that caused leaks. And leaks were a problem because water was leaking and we built our houses in air. This is actually one of the benefits of using a forced air system, right? Our builders, our contractors, us, we don't notice when we have an air leak because we build our buildings in air. We notice if we leak too much cold air onto a surface and mold starts to grow or something like that. But it's just an interesting perspective that water leaks we notice because we don't build in the water. But the bottom line is that when we use water to pick up the heat instead of air, we have a much more energy dense fluid, right? It's 832 times the density. It can hold much more energy. So that's the basis of a radiant system, is to use water. And it's not actually that different than air. I mean, the fluid is water instead of air. You're using pipes and tubes instead of plenums and ducts. You're using valves instead of dampers. You're using pumps instead of blower motors. One little subtlety here is that in an air-based system, you really don't want much turbulence in the line. This is why designers like us work so hard when we do air distribution system design, is because we don't want turbulence, because we want our air to go into the duct with a certain psychrometric condition and leave the duct with the same psychrometric condition, because the business end is in the air, not in the duct. Whereas in a water pipe, I want turbulence. I want that liquid to be encountering the walls of my thermally connected surface, which is the walls of the pipe, so that it can absorb energy and release energy, depending on whether it's heating or cooling. One little quick interjection there. When it comes to the airside systems, we know what condition will make people comfortable, right? So we know that if you put around 30 BTUs of energy into each pound of air, people will stand in that and be comfortable. And it's interesting, I said energy, I really mean enthalpy. And enthalpy is a combination of the heat and the humidity in the space. So when we talk about, the air conditioner is supposed to be set at, the optimal, let's say, ANSI guidelines are for 75 degrees at 50% relative humidity, which is 63 degree wet bulb. That's going to correspond to something like 30 BTUs a pound. That's a little geek out on the side there. So back to where we were going, what they're doing is they are harvesting the heat or supplying the heat through a high density fluid.
Can you tell me a little bit more about the process of radiation?
Yeah. So we know radiation, right? So you hold your hands in front of a campfire and the heat is radiating to your hands. The air is, let's say it's winter, right? It's 20 degrees out and you're standing in front of a campfire. The air is not heating you, the radiation is heating you. Notice that the radiation is only mildly heating the air between you and the fireplace. Better way to think about that would be to think about the temperature of non-air, right? There's very few molecules per, I guess, even square mile in space. Spaces are on the order of negative 450 degrees Fahrenheit. It is extremely cold. And yet there are huge amounts of solar radiation traveling through space, right? The Earth only picks up a small arc of the total actually steradian angle that is coming out of the sun. And that small little bit of radiant energy from the sun, it travels across 93 million miles of frigid cold space, hits the Earth, And what does it heat up? It doesn't heat up the air. I mean, mildly. It hits the atmosphere. Heats that up a little bit. But the reason it's hot on a summer day is not because the air is hot primarily. The air is hot as a secondary factor. What happens is the radiant energy comes down through our atmosphere, mildly interacting with it, hits the dirt or the water. There's a lot more mass there. It heats that mass up and re-radiates that heat to any colder surface around it, which is now the sky. So in a very similar way, let's say I want to be comfortable inside my building. That means I want my body to have the ability to regulate its temperature. And if it's summer, I want to make sure that the walls around me don't find me as the cold surface. Because if I'm the cold surface in the room, then I am going to be downhill from the heat energy in the window, let's say. Like the glass gets hot, that heat needs to go somewhere. Where does it go? Any cold surfaces in the room. Where are those cold surfaces? Well, they're all over. If the air conditioner is doing its job, it's rinsing those surfaces. It's rinsing me. So the worst place for the heat from the glass, the solar radiation that made it into the building to go, would be my skin, and it will go there. It's indiscriminate. It goes to the coldest surface. Similarly, or I guess conversely, in the winter, it's cold out. The glass surfaces are cold. What's going to happen when my skin is exposed to a cold glass surface? My skin is warm. The glass surface is going to, I'm going to radiate to the glass surface. It's going to feel like the glass surface sucks heat off of me, but there's actually no such thing as cold. There's just heat and less heat, and it always moves from more to less.
So to summarize that idea, and I want to make sure I'm understanding it correctly, the idea of using air to heat and cool people in a space is less efficient, and physiologically speaking, less efficient than using the surface temperature to achieve the same goal. Is that right?
Absolutely right. Absolutely right. And if you heard our previous podcast on the history of air conditioning, you'll find conspicuously absent from that discussion was, well, air conditioning was used because it's the most rational way to condition people. It's actually, we're conditioning volumes of air in a building, and hopefully as a side effect, conditioning people. And I want to throw in here, I don't want to sound too down on air conditioning. I mean, it basically works, right? So there are, millions of homes, hundreds of millions, like 120 million homes in this country, plus all the commercial buildings, most of them using forced air, mechanical heating and cooling to condition them. And for the most part, people are happy with it.
And it absolutely has given rise to an entirely new way to live, right?
Exactly right. But as someone who's been lucky enough to be inside radiant controlled spaces in Europe and other places, it's as though it's like a 1950s car, right? If you've only ever driven a 1950s car, well, it's doing fine. You know, it gets you from place to place. Maybe not 50s. Let's say a 70s car. Let's say you've only ever driven a 1974 Plymouth Duster, but it had air conditioning, right? So it starts, it rolls, the windows go up and down, drives down the road. That's the only thing you've ever driven. You're good. You get into a new car, right? You get into a Tesla or, you know, whatever your favorite car is. You get into that car. Now you go back into your Duster.
Especially if it has those nice seat coolers and heaters in it.
Exactly.
Right?
Oh, there you go. Some more radiant.
Yeah.
Well, actually, if you're sitting on them, it's conduction. But you know, so the bottom line is that getting back to the human factor design, fundamentally, what are we doing with our cars? We're making tremendous strides in ergonomics, in designing the space around the occupant of the vehicle, of the car, to meet human factors and human needs. That's what we're doing. Buildings are woefully behind and need to catch up.
And it's not as though we're not in a place to be ready to design systems for homes like this, but especially in the US, there is a lacking market infrastructure. We need more people manufacturing these things. We need more people distributing these things.
We need more people asking for these things.
Absolutely. And that leads to the biggest piece that we probably all think of, which is people who are able to install these things, right? That's a big worry for a lot of people. They don't feel comfortable with the person who's doing the job. They're definitely not going to pursue the technology.
Most people, when they get an air conditioning system installed or a heating system, you know, when I'm the contractor and I say to you, well, what I recommend is, well, implicit in what I recommend in those words are a lot of factors, right? What I recommend means what I know. It means what I don't know. It means what I am thinking I can make some profit on. And what it means what I think can be fairly transactional with you. So there's just got to be a larger discussion around what is it we're really shooting for as a society of people working together. Radiant systems have the ability to make people more comfortable, and at the same time do that while saving energy, right? And saving energy is in fact a human factor. You could argue it's a tremendously potent human factor in the sense that many geopolitical conflicts right now on the planet are around scarce resources, scarce energy, scarce water. If energy was more abundant, or if we were using it differently, you know where this is going. You guys can all hear it. But back to the radiant heating and cooling example. Radiant heating and cooling is designed around what's called low temperature heating, high temperature cooling.
Could you explain that a little bit? Because that seems a little counterintuitive.
It seems flat out counterintuitive, yeah. I didn't say it wrong. I said low temperature heating, high temperature cooling. Let's talk about the heating part, right? So on the heating side, if you have a radiant system, you have a good enclosure, right? So we talked about that before. The enclosure in the mechanical system, it's one machine. It's an artificial distinction. We don't go drive around our chassis engine thing. We just drive around in a car. But so if we have a surface in a radiant or thermally active surface in a building, and it's heating us, and it's a good building, we don't need to go much above, well, we can go right around 80 degrees, upper 70s, low 80s, right? So that's it. We need to bring that surface to, let's say, 80 degrees. Think about a gas furnace. You bring a flame, you cause a flame to exist, which is around 3,500 degrees Fahrenheit, in order to bring air to around 140 degrees, 150 degrees Fahrenheit. And then you introduce it into the space to bring the air temperature, when it's all said and done, to around 65, 70, 75 degrees Fahrenheit. So that is high temperature heating. Whereas in a radiant system, ideally I could just use, even in the wintertime, I could just use a solar absorptive water heater to collect heat from the sun and circulate it through pipes, right? No compressor. I mean, this idea of compressorless comfort and compressorless home performance is one that we as an industry are definitely moving towards, and a lot of people don't realize it. Let's go to the cooling side now, right? So remember, it was low temperature heating, high temperature cooling. The low temperature heating is around 80. The high temperature cooling, you need surfaces, again, in a good enclosure around 60 degrees, maybe the mid 60s, not the mid to low 40s, right? Or even the upper 30s where some air conditioners can go. And by the way, they're limited there, of course, because we don't want them to freeze up. They're definitely going to be condensing water. You get close to freezing, you get ice, that blocks the airflow. Now you have runaway freeze up. That might have happened to some of you that are listening. So low temperature cooling, you have a good building. You don't need to go above, let's say, the low 60s, even the mid 60s. Where can you find that temperature? Under the building, in the earth. So again, you could run a pump, circulate fluid, do heat exchange with the ground, no compressor. I mean, there's a lot of areas where that won't work, but certainly the reliance on compressors is a lot less.
So to think of this in relation to the human body and the idea of thermal comfort, I'm reminded that our bodies are using this homeostatic system and trying to maintain a core temperature and optimize our fuel use, which is your fat stores and the food you ate. And the body tries to do this by minimizing the rate of heat exchange that occurs, right? And so I'm reminded of the spring-fed river that runs through the town where I attended university. I'm sure you can imagine we skipped a lot of class because it was a beautiful, crystal clear river, but that's another story. But in the wintertime, we would go to this river, and because it maintained this constant temperature of 73 degrees on a very cold winter day, you would feel really chilly until you got into the actual water, right, at 73 degrees. And the delta T between your skin and the water was almost zero. right? You felt comfortable in the water because it was warm enough for your body to understand it, feel comfortable. But the moment you would bring your head out of the water and the steam starts coming off of your head, especially if the breeze was hitting it, you felt immediately cold because your body was just experiencing rapid heat exchange. So the idea is when we dive down on a winter day and come back up, our heads are radiating heat very quickly back into that cold space, right? And in the same scenario for a summer day, our heads come back up and they absorb heat really quickly. In either scenario, the body is striving for that homeostatic balance. It's very sensitive to that heat exchange process.
So what's happening in your example, that was a good example there. When you're underwater, the entire surface area of your skin is experiencing that water temperature. And by the way, it must not have been radically different from comfortable skin temperatures, which is probably in the mid 70s or something like that. And this can relate to radiant heating and cooling in the sense that if you want to have high temperature cooling and low temperature heating, one of the ingredients for that is to have a large area radiator. So if I have, let's just look at relative radiator sizes. Or in typical air conditioning system, you have a heat exchanger that gets cold and it needs to condition all the mass of air in the house. So how big is that heat exchanger? Well, it's about as big as a radiator in a car. So let's say 2 feet by 2 feet, just to pick a number.
Not big.
So not all that big. So because it's not all that big and it needs to convey a lot of energy exchange, it has to be very, very cold. And also the reason it has to be very, very cold is getting back to the fact that it needs to convey a lot of energy exchange through air, which is not very dense, right? So you have low density fluid with a small area radiator being used to transfer the heat or the cold. Therefore, the temperature has to be very, very low in the cooling mode, and everything flips around in heating mode. Well, if I have the entire ceiling of the room, which is a fantastic place to cool from, then I have a very large radiator. That means I don't need to have it be very, very cold. It's just a very basic concept. In fact, thinking about the concept of basic concepts, is there's a lot of rhetoric in our world these days in the category of technology will save us that gets morphed into technological mumbo jumbo will save us. And if someone can't explain to you in a very simple way why their system works, they probably don't understand it very well, and you might want to be wary. I think Einstein might have said that.
It sounds like Einstein.
Somebody said that.
He probably said it in German.
Yeah, he said it in German. So this idea of low temperature heating and high temperature cooling is intimately tied to the area of the heat exchangers. By the way, it doesn't have to be the ceiling. It could be the floor. It could be the walls. Radiant heat exchange can occur through aftermarket panels that are external to the ceiling. It can occur through a combination of air and radiant. You could have a radiant heat exchanger that actually has a fan that blows air across it to move by convection to move the air around the space. Let's see. Oh, convection. So let's say I do have the ceiling cold and I'm here in Austin. A couple of really important points to talk about. One is that hot air naturally rises. I mean, we've talked about that. Heat doesn't naturally rise, but heated air floats on cold air. So in this room we're in, the ceiling is where the hottest air is going to be, just naturally. It's just the way it's going to happen. It's always great to rely on natural properties of physics. So one of them is that the hot air is going to be at the top of the room. So if I have a cold surface there, the hot air is going to go hit the cold surface. It's going to get more dense. The surface is going to absorb the heat, take it outside, and the air is going to fall. So a radiant cooled ceiling is going to have like a very mild drizzle of cooled air constantly moving down across you. So that means you don't just get the radiant effect, which keep in mind, radiant effect is line of sight, speed of light, has nothing to do with the air. But you get this additive effect of the convective or the air moving past you cooling that's occurring. Here's a big one. Somebody listening to this podcast has been wanting to raise their hand and ask this question. And it's about, but what about condensation on the surfaces, right? So we have thought about that, and there's a couple of answers. One is, done right, the surface temperature for radiant cooling does not get near the dew point in the space. So that's probably the anchor man. And there's like, don't worry about it, done right, You're not going to have a ceiling cold enough to reach dew point. You are going to have sensors on that if your occupant opens the doors and windows and allows the outdoor environment to come in, well, the surface has to heat up. And done right, again, you're going to have insulation between your radiator and the space, so the insulator is more coupled to the space so that it can change relatively quickly. It changes temperature. But more so, and this is something that our design shop at Positive Energy has been doing for years, is we recognize that the strategy of not having a dedicated dehumidification system or not having a dedicated system to control the humidity of a space in a hot, humid climate, it's unrealistically optimistic and has been for quite a while. Especially as energy codes change, it becomes more and more unrealistic.
Because that humidity does actually constitute embodied energy itself, right?
And that's exactly right. Like you spill a cup of water on the table in front of you, what happens tomorrow when you come back? Well, you might have a spot on the table, but the water is gone. Where did it go? It didn't magically vanish. It evaporated molecule by molecule. What did it do? It absorbed the heat from the space to change phase from liquid to vapor. Keep in mind, vapor just means a gas near a phase transition. This is why we don't say that air is made of nitrogen vapor. We say it's made of nitrogen gas because it is nowhere near the phase transition to liquid. However, water in the air is near the phase transition point, so we call it water vapor in the air. So let's say it's 1 pint of water, weighs about a pound. It's going to take 1,000 BTUs of heat from the room that you're in to make the transition from liquid to vapor. So what does that mean? That means when the liquid evaporated into the air, it actually is stored heat. That's why you say it's the heat and the humidity that makes the comfort problem.
So to summarize where we've come from the beginning of the show to now, we're talking about a really complex technology, and as you can probably see, we could go on for days and days about it, and how really powerful and incredible it is. And at its core, it's simple, right? And it's going to change the way that buildings operate. And the most amazing piece is that it's perfectly aligned with the notion of human factor design.
That's exactly right. And, it gets better, actually. It gets better in the sense that the way buildings are conceived get defragmented. Right now, there's this artificial distinction. We see it all the time where somebody designs a building, it gets handed off like a baton at a relay race to somebody to design the mechanical system. That is a really unfortunate, ultimately energy inefficient, uncomfortable way to do buildings, and it's going away. The less wonderful news is that just as market forces led to the supremacy of forced air heating and cooling systems till now, market forces are in fact, they exist. And I'm here in Austin. Boy, oh boy, there is no one distributing products that I'd like to design with. And even if there were distributors, who am I going to get to install it? The answer right now is no one. I'm really excited to say that we work with some amazing contractors here in Austin that, I can't help but talk about this stuff over the last few years, and they're ready. So what we need are architects to be ready, and I'm pretty confident that some architect out there is going to have a client that says, I get it, I hear what you're saying, it makes sense. I understand that I have to go to New York or Canada or Seattle to get the equipment, but you know what? It can be drop shipped to Austin, and the laws of physics are the same here, and it's going to work.
Just because we're talking about this new paradigm of heating and cooling a space is not to neglect the fact that we still need to treat air, because people are going to be inside those buildings, and as we all know, or hope, people breathe air. And that's a really important thing to remember. So, disclaimer right now, we're not getting rid of air. We're reducing our reliance on its inefficiency and focusing on a new technology that enables us to really rely on something that's very energy dense and that can make a big difference in the way that we build homes.
Right, exactly. We're still using air. We still breathe air. It still goes into our lungs to help our body deal with its internal combustion cycle. Actually, we exhale. It's like the exhaust pipe of our car. But what we're using air for is breathing. So we're going to filter the air. Even though we have a thermally active surface in our building that's our primary heating and cooling mechanism, we have a secondary system that is air-based, and it's accomplishing filtration, right, for breathing. It's accomplishing dehumidification.
Especially if you've got a dedicated unit.
Exactly. And it's accomplishing mixing and ventilation, outdoor air coming in. So the good news there is, though, that the quantities of air on these systems, think about it, for breathing and ventilation, those are, 50, 60 CFM, 100 CFM in a giant house, and it's a lot more in commercial, but it's many times less, orders of magnitudes less than the amount of air we need when we use air to condition the temperatures of the surfaces around us, right? So if we take away that job from the air, we end up with a much reduced role for the air to play and more focused on what it does, right? So what that means is we can spend more money on the air side system since it's smaller and it's moving a fractional amount of air, and we can have much better filtration, more robust filtration that actually works and gets us better indoor air quality overall.
And the coupling of these two technologies, both reduced need for air and thermally active surfaces in terms of energy use, is like the difference between a thirsty teenager drinking a Red Bull on a summer day and your grandmother sipping some kind of herbal tea, right, in the winter.
Exactly.
And the speeds are going to be very different, right? We want to think about our energy use in much more meaningful ways, and this is absolutely a way that we can do that.
Yeah. So hope you guys enjoyed this podcast. There's more to say, and we'll be bringing it to you next time.
Thanks so much, everyone.